early on a Monday morning to hear about some of the integrated planning issues. So welcome everyone to Tucson, and hope it's going to be a good week, a lot of good discussion. This hopefully will be a good start to the week. Those of you who aren't aware, there's a GPST event next door, so if you're looking for that, it's in the other room over there. This is the tutorial. So the intent of today's tutorial, as you'll see in the agenda, is really to look at integrated planning issues. This was suggested by some of the members around something that could be a useful thing to look at, what companies are doing, what capabilities are out there, what some of the kind of research type stuff that's going on. So the first hour or so here, Anish and Elaine from EPRI and NREL are going to talk through some of the work that's going on, more in the research kind of space, and looking at some of the kind of advanced capabilities happening there, and talking about kind of what the frameworks need to look like and what tools and data and other things are needed. And then just after the break, we'll have Andy from GE kind of continue that longer discussion around some of the tools we use at GE. So we'll have 3 longer discussions, 30 minutes or so each. And then we have a panel with 4 others that are either practitioners, tool developers, utilities, others that are actually ISOs that are working on these topics. So there'll be shorter presentations, which will allow for some discussion at the end. The intent of these tutorials is really to get into a little bit of the details and really understand some of the concepts. So don't be afraid to ask questions. Definitely the intent here is to learn about what people are doing. So the first speaker is my colleague Anish Gaikwad. So Anish, work closely with Anish at EPRI's Grid Operations and Planning Group. He's a senior program manager. He leads our transmission planning research area, working with members to develop and execute on R&D plans and research portfolio. He's also co-lead of the Integrated Strategic System Planning Initiative. He's going to talk about here and provide strategic input to our Climate Resilience and Adaptation Initiative that started last year. He's a group of about 25 modeling and simulation experts that work on these topics. So Anish will give us the overview of some of these integrated planning activities.
Yeah, is it better? Thank you. So thank you, Aidan, for the introduction. So my intention today is to lay the groundwork for the integrated planning. How many of you have heard the term integrated planning or are involved from your utilities side? Okay, that's good. So what I'm going to do for next 30 minutes or so is to present the framework that we have been working on for almost 2.5 years. Doesn't mean this is the only way of doing things, but I wanted to lay out what we did in past couple of years or so. And then, as Aidan mentioned, feel free to have questions. I would definitely like to have more dialogue going on because, as I said, this is not the only way of doing. So happy to hear your thoughts as well. So in terms of why, I think this is preaching to the choir, but why is because of all the changes that are happening in the system. Right from the resource side all the way up to the end use side. So as we are embarking on these decarbonization pathways, some of the fundamental questions we need to address are, what are the right ways of doing things? What is the right resource mix? What is the right technology mix? So that's the first fundamental question. The second fundamental question is the scenarios that we will come up with for 2035, 2050, whatever year you are aiming for. How do we ensure the reliability and resilience of that future? How do you ensure that the choices you are making today will be reliable 15, 20, 25 years from today? And that's the crux of why something like integrated planning can play an important role. If you look at the graphic on the right-hand side, those are the 4 circles that I'm showing. Starting from the top left, where we are looking at how to build the scenarios, and that is impacted by the policy decisions that we are having at the state level, federal level. So starting from that high level view of the system, how do we link that with some of the reliability assessments that we have been doing in utility, like resource adequacy, production costing, going further down into transmission, distribution. So the circles themselves, a lot of work has been done over the decades in terms of the reliability assessments, developing scenarios and all. The challenge is how do we link all that? Like for the most part, those things are happening in silos in utilities. I mean, you have like an integrated planning department, which is different from transmission planning, which is different from distribution planning, and they may not be talking to each other. And not just literal talking, but also in terms of the data that needs to be exchanged. So one of the, if you have to take one, if you have one takeaway from this presentation, it's about linking all these different facets of planning that is happening in the utilities. And that's the reason we are thinking about integrated planning. So this is my second takeaway from today. If there is one thing you want to remember, then probably this is the graphic that you should remember. So the rectangles there, they represent different planning processes that are happening in the utility. At a very high level, there are three buckets that you can see on this slide. Starting from the left, there is scenario development, which I was talking earlier, that if you're looking 15, 20, 25 years in future, what are the technologies you need to consider, how much renewable, now hydrogen, from the resource side, as well as from the end use side, electrification of transportation, electrification of industrial processes. So all that goes into the scenario development, which is influenced by markets, which is influenced by the policies that are being formed and so on. So that's the first bucket. The second bucket is once you have the scenario built, how do you come up with the expansion plan for that scenario? Where to place generation, where to build transmission. So that's the second middle bucket, which is around capacity expansion. Once you have your capacity expansion for future, then the next question is, how do you assess the reliability? And the rectangles that I'm showing in the rightmost column, they are some of the processes that most of you are familiar with. So you have an expansion plan, then you do the reliability analysis in terms of resource adequacy, in terms of production costing, in terms of transmission reliability analysis. And last but not the least, the distribution as well. There have been some studies done in recent past where they have looked at most of the blocks I'm showing, but distribution has not been considered in as much details that it deserves. So I wanted to emphasize that distribution, it's not like that end piece of the puzzle, but it's very much an integral part of the overall integrated planning process. So the main work that we did is not so much around the blocks that you are seeing, because they are more or less, you're familiar with them. But the most of the work is around establishing these arrows, the bidirectional arrows that I'm showing here, in terms of what linkages need to happen across various planning processes, how to exchange the data, also the feedback loop, as I will talk further down my presentation. Once you assess the reliability of the expansion plan that you have, what feedback you need to take from here all the way up to here and maybe even here. So having those feedback loops established, that is also a critical piece of the entire process. Just one quick note, as I said, this was an internal EPRI initiative. So we had only limited time and limited budget. So we could not establish all the linkages that I'm showing here. So whatever I'm showing in red, that we did not explore more. I will get a little bit into the details of that. But as such, this is the entire framework. If we have to do an actual case study, this is the framework we could start with. And again, as I said, maybe not the only way of doing things, but that's the approach we took. So for rest of my presentation, I'm going to explain each one of the three buckets, what we did there, and talk about the final results that we came up with. So we did a case study for New York ISO, and just to make it very clear, we did not actually work with New York ISO. We had data available from New York ISO. So we used that data for the case study. And the case study was just to demonstrate this framework. The intention of the case study was not to make any planning decisions or not to make any investment decisions. As I said, ISO itself was not involved. So again, the case study that I'm going to talk about It's not an end in itself. It's a means to demonstrate the framework. So whenever you see any numbers, any cost numbers I'm showing, take it with a pinch of salt that they are only for demonstration purposes. So with that, and this is one of the challenges with integrated planning. So what I'm showing on this slide is the list of tools that we used for each one of these blocks. So for example, for coming up with the scenarios, we used a tool called Regen, which is an EPRI research tool. Other entities, they have similar tools. I know NREL has Reed's tool, which has comparable capabilities. But anyway, the point is we used Regen to do the scenario analysis. And going down, we used Plexos LT for capacity expansion and Plexos for production costing as well. Then PSSC for transmission reliability analysis, and Drive, which is again an EPRI tool for distribution analysis. So the challenge is, if you look at the scope, the transmission scope, some of these models, they have zonal representation. Some of the models, they have nodal representation. Also in terms of the temporal resolution, some models, they work for every hour of the year, like production costing. For some others, you can have only the slices coming out of the 8760. For those of you who are familiar with PSSC, we use only snapshot analysis. We pick particular cases and so on. So that's one of the fundamental challenges in terms of the spatial scope, as well as in terms of the temporal scope. And again, just to make sure these are the tools that we use, doesn't mean these are the only tools that are available, but any tool that you will use for doing these analysis, you will face similar challenge. And that's where one of the gaps there is right now. So in terms of the case study itself, as I said, the case study was only for the demonstration purposes. So we asked the question for the state of New York for the year 2035, how can we assess the reliability of that future year? And we looked at what we call as the reference scenario, which assumes all the state and federal policies, state policies like their CLCPA policy. So everything on the book that remains for the year 2035, but it doesn't go anywhere beyond that. So that's the reference scenario. And then we also looked at deep decarbonization scenario, where we went a step ahead of the reference scenario and looked at zero carbon for the energy sector for the state of New York. And we also assume the federal regulations are in place and so on. So this is definitely much more aggressive scenario compared to the reference. And the question we asked is, how do you go about it? How do you assess the reliability of each scenario and essentially demonstrate the framework? So starting with the development of scenario. So that this is the first block starting here. So as I mentioned, we had this US Regen tool, which has a high level representation of the entire US power system. So as you can see, the graphics is showing US is the 48 states, they are divided into 16 zones, and we assume pipe and bubble representation amongst the zones. So it has a fairly detailed representation of the energy resources as well as the capacity requirements for each one of the 16 zones. It also takes into account state, federal policies into account. In addition to the resource representation, it also has the end use representation in terms of electrification across residential, industrial load class, in terms of the policies that are occurring on the resource side as well. So essentially, it's a high level view of the resource side and high level view of the energy use, end use side. And it tries to have a co-optimization between the two to come up with the best scenario. So, and the output of the process is in terms of the technology blocks, how many gigawatts of wind, how many gigawatts of solar, how many gigawatts of electric heating on the end use side, and so on. So the bottom line is, a tool like Regen, it can provide a good starting point for the future that you are envisioning. So you can obviously have your analysis without something like regen, but if you have a tool like this, then you get a good starting point rather than trying to guess what might happen. So that's the biggest advantage of having something like regen. So again, as I mentioned, don't worry too much about the exact numbers that I'm showing here. The main point here is for the reference scenario and for the deep decarb scenario, this was the resource portfolio that we came up with. So as you can see, for the deep decarb scenario, there is significant bulk connected solar, significant wind. There is hydrogen as a fuel as well. So we came up with the scenarios for reference as well as decarbonization case for 2035. So that was the starting point. Next, we took that scenario and got into the capacity expansion, which is the middle block I'm showing here. So the capacity expansion was done at the nodal level. So one of the linkages that we worked on is to start with this high level zonal representation. And again, we focused only on New York, but for the state of New York, take that information at the nodal level to place the generators within the New York footprint. So again, we developed a bunch of Python scripts to do some automation. We also had to assume locations where those generations might come in and so on. So that's the first linkage we established, linking the zonal scenario with more detailed nodal representation for capacity expansion planning. And as I mentioned, we use Plexos LT for the capacity expansion. So once we had, and this gets into a little bit of more details. So the inputs that we used and the outputs that we used to link regen with Plexos LT. Looking at the profiles, looking at fuel cost, some of the other constraints like CO2 constraints and so on. So we took all that information and linked regen with Plexos LT. And once we did that, this is the refined scenario that came out of Plexos LT tool. One thing to note here is we assume New York is an islanded system when we did the capacity expansion. So you don't see any imports there. And that was a more conservative assumption that we don't want to rely on our neighbors. So we just assumed there are no imports. And as you can see, again, that there is significant wind that includes offshore wind for New York as well. And then there are other portfolio as well. So again, the lesson or the takeaway here is you start with the high level scenario, you run it through the nodal capacity expansion, you come up with a more refined representation. And then the next question is, now you have your capacity expansion plan. How do you assess the reliability of that capacity expansion plan? And again, we went through all the processes, which I think most of you should be familiar with: the resource adequacy analysis for planning reserve assessment, production costing runs to look at the economics, getting into power flow and stability considerations. Although we didn't get into stability in this particular efforts, but you can obviously do stability analysis and going further into distribution. So I could be spending next 1 hour just going through each one of these, but given that we don't have time, let me just summarize the reliability analysis that we came up with. And I'm going to focus only on the deep decarbonization scenario. So once we started with the plan that I was showing here from capacity expansion, the first analysis we did was to look at the resource adequacy. And we used 0.1 days per year LOLE criteria. And the capacity expansion plan we had, it did not meet that. It didn't have enough reserves in the initial plan. So the feedback action, the recommended action was obviously to increase the reserve margin. So we increased it to 16% from the initial one, which was 8%. We also looked at role of energy storage. So we tried to look at longer duration energy storage, like 6 hours or so. I think that was the size of the batteries. And that also helped resource adequacy assessment as well. So those two were performed under resource adequacy, looking at the planning reserve margin as well as looking at the role of storage. Then after that, we passed that information to production costing analysis, which was the hourly run, again performed in Plexos. And sure enough, we did find some constraints, the transmission constraints in our PCM analysis. So again, that kind of triggered upgrade of the capacity expansion plans in terms of upgrading the transmission. So we looked at transmission from economic standpoint in the PCM analysis. And then after the PCM analysis, we linked, we also looked at operating reserves. So in the RA analysis, we looked at planning reserve, but as part of PCM, we also looked at operating reserves required for flexibility as well as for contingency. For this particular case, we did not see any issues with operating reserves, but again, that's just for the case study. So again, steps 3 and 4, they were part of the production cost analysis. And the last step was around transmission reliability assessment. So we linked our PCM analysis with transmission planning cases. And I know one of the next presentations, they are going to go into further details. I will also quickly talk about what we did in terms of linking PCM with transmission. But anyway, so we looked at some snapshots in transmission. And sure enough, there were needs from reliability perspective. We saw thermal overloads, we saw voltage violations, and we added more transmission reinforcements to get rid of those violations. So, so those were the 5 steps that were performed for assessing the reliability of the deep decarb scenario. So next few minutes, I will just spend on linking the production costing with transmission planning linkage. Again, we can get into more details. So the idea or the question here is, if you have 8760 runs coming out of production costing tool like Plexos, or it could be more than 8760 if you're considering multiple years, then obviously you cannot run transmission analysis on each hour, right? So the question is, which hours are critical from reliability standpoint? So in order to select those hours, we came up with a framework, we call it as high-level screening, or HILS for short. And we look at some of the characteristics of the system. So in this particular example, we looked at, for each hour, we looked at total generation, total wind output, solar output, total system load, and there are some other variables that you can look at. But essentially, looking at these variables, and we used a statistical clustering technique, specifically using principal component analysis and silhouette analysis and k-means. So essentially a statistical approach to cluster the 8760 hours. So each color here that represents the set of hours coming out of production costing that have similar characteristics. So now you can look at the clusters, and then from each cluster, you can pick one or more data point to build your transmission planning case. So that's the concept we use. So starting with 8760 snapshots, ending with a few representative hours that are critical from reliability perspective. So again, that's just a graphic. You may not be able to read, but essentially for this particular case study, we came up with 5 clusters, and you can read the description of each. To demonstrate the process, we picked representative data points from these 2 clusters. So we looked at scenarios. So this is the x-axis is load, y-axis, that's the renewable megawatts. So we looked at one PSSC case where load is low, but renewables are high. And we looked at another case where load is also high and renewables are high as well. Again, this is just to demonstrate the concept. You could be picking more data points as well. And then for these 2 scenarios, we looked at transmission reliability assessment, what transmission reliability needs in terms of voltage violations, thermal violations, and so on. We didn't get into stability, but obviously, once you have the scenarios picked, you can also run the stability analysis as well. And one point to make here is this analysis just tells you which generation dispatch and load level to pick. There is the manual step of actually building the PSSC case. And for those of you who have actually done that, either for PSSC or PSLF, you know the manual process or the pains that you have to go through to get the solved power flow. So again, that's a lot of that is manual work and that requires time. So anyway, coming back to the last part of the analysis, looking at distribution as well as looking at the feedback coming out of the reliability analysis. And I will talk about both very quickly. So in terms of the feedback or the corrective actions, as I mentioned before, when we used the initial expansion plan, we found out that there was not enough planning reserve margin, so we rectified that. When we ran the PCM analysis, we found that there were transmission lines that were constrained, thermally constrained, so we reinforced the system. We used PSSC to look at voltage violations as well, so we looked from the reliability perspective. So all that feedback was passed to the expansion plan, and the expansion plan was modified. So that's one aspect. The second aspect is looking at distribution, because so far we had not looked at distribution. And this was quite a bit more challenging, and this is a practical challenge as well, because we could not get the distribution models for the entire state of New York. And as you can imagine, with so many distribution utilities, having a very detailed model of each distribution feeder, it's an insurmountable task, if not impossible. For this analysis, we did not have a lot of distribution. So we looked at only representative feeders, and I will get a little bit into that. But before I get into distribution, just wanted to show you the final result. And again, let's focus only on decarbonization scenario. So this is the initial portfolio that came out of the initial expansion plan, and this is the final portfolio of resources that is after accounting for all the feedback from the RA analysis, from production costing, from transmission, and so on. Again, just cautioning you, don't worry about the actual numbers you are seeing. The point here is you can keep refining till you reach the final answer by going through this framework. And again, you can look at the operating cost and the fixed costs. Actually for the reference scenario, the operating cost actually reduced for the final scenario and so on. But again, those details are less significant. The main message here is, as you keep refining your analysis, you can see changes in your operating and fixed cost compared to your initial scenario. So, and this again shows within New York, the additional transmission that was required, as well as the circles here, they represent transmission that is required within that zone, and the arrows represent transmission between the zones. So again, you can get that sort of information once you go through this iterative process. Also, within each zone of New York, what happens to the generation when you add transmission into consideration? So in some cases, the initial plan had more wind, but after you build transmission, not so much wind was required. So that's when the arrows are going down for each technology. So I'm showing solar, wind, gas, hydrogen, and others. So the point here is, once you add transmission, that can change the generation profile within each zone. So then now coming back to distribution, as I said, we did not have full distribution model for the state of New York. But to complete the analysis, we looked at 124 feeders, which were not from New York. We had those models for some other utility, but we assume they're for the state of New York. But again, the emphasis is on the concept, not so much on the numbers I'm going to show. So the first thing is, the question we are asking here is, can you do something on distribution that will change your expansion plan? So can you have more DERs on distribution that will change your resource profile? Can you have more distributed storage on distribution that will change your final expansion plan? Those are the type of questions that we need to answer. And the starting point for that was, we looked at 124 feeders, which had 11 substations, and just starting with the hosting capacity of the existing feeders. So this is the 2020 system, which was the starting point. And we just ran the hosting capacity on each feeder. And as you can see, or you may not be able to see, but some feeders, they had very low hosting capacity already to begin with. Some had significantly more hosting capacity. But again, that gives you a picture of your system as is, and then you add your growth profile. So I may not have a slide here, but so what we assumed is we started with 2020 and then going all the way up to 2035, we assume growth rate and we assume penetration of DERs on distribution. And that information came from the top, that information came from the regen tool I was describing. And that's another salient feature of this integrated planning, that all the assumptions that you make from the start, they flow down all the way up to end. So whatever growth rates you assume in your scenario, they will flow down all the way up to distribution. So that there is no discrepancy in what you assume on distribution with what you assume for building the scenario in regen. So in terms of the distribution, as I said, we started with the baseline. Then for the scenarios, we took the information from the regen tool in terms of the renewables, I mean, the DER growth as well as load growth. And then we looked at what happens to the distribution system as you start adding DERs and loads. And again, I will focus only on the decarbonization scenario. So obviously, as you would expect, adding more loads and DER on distribution, that caused violations on those feeders in terms of either voltage or thermal violations. And then we looked at different options, specifically non-wires alternatives, looking at distributed storage, looking at demand response, and you can come up with cost for having those non-wires alternatives. We also looked at actual steel in the ground type of upgrades on distribution, like what if you add new feeders, what if you add new substations. Obviously, that's the most robust option, but that's also most expensive option because you are actually adding stuff. But certainly there is value for non-wires alternatives like storage and demand response, which may be relatively less expensive and may still do the job. Again, as I said, this was like a very, very partial analysis because we looked at only 124 feeders instead of the entire state of New York. And that's the reason we did not add these costs in the overall cost that I was showing earlier. But the main point is not to forget about distribution, and there could be some decisions on distribution that can impact your overall system plan. So I have only 6 seconds left, so I will quickly wrap it up. So 5 lessons learned. As I was mentioning, regen, having a tool like that, it gives a very good starting point in terms of building the scenarios. And again, I'm not saying regen is the only tool, there are other tools as well, but starting with a good assumption that helps. Then the second takeaway is what I was explaining earlier, that linking your zonal model with your nodal model, that definitely gives, and that's what we did by linking regen with Plexos LT, which was nodal. That gives a very good starting point for further analysis into production costing and transmission. So linking your zonal analysis with nodal, that was the second takeaway. And then I talked about all the reliability analysis that we did. So it's a multi-directional view. You look at resource adequacy, you look at production costing, you look at transmission and distribution. So you cannot just focus on one aspect. You have to look across everything to make the reliability-based and economics-based decisions. Then the link between production costing and power flow, as I mentioned, we had that framework that is also essential to identify what are the critical snapshots to analyze in transmission. And then the distribution as well. So in addition to these 5, a couple of things I wanted to mention is 80% or even more than 80% of the time was spent on data. So getting the right data, massaging the data, establishing the linkages across the tools, that was more than 80% of the efforts. The second takeaway is computational time. I mean, you really need high-end computational power to do some of this analysis. Otherwise, there could be a lot of bottlenecks in the process. And the third thing, it's not so much technical, but it's about the culture that within the utilities, we need to break the silos, that transmission planning needs to talk to long-term planning, and they need to talk to distribution planning and so on. So it's also about breaking the barriers so that there is free exchange of information from the utility side as well. So let me end on that note. Yeah, one last thing. So everything is publicly available, what I said. So there are 7 deliverables that are coming out of this effort. They are not there yet, but they should be available very soon. And you can keep this website for your reference. So there will be 7 PowerPoint presentations to summarize the work. They get into different topics that I'm listing here, but you are more than welcome to take a look at these once they are available in next few days. So with that, Aidan, let me hand it back to you.
I want to be up to next speaker. Elaine Hale. Elaine's a senior research engineer at the Grid Planning Analysis Center at NREL. So she will talk about a very similar set of topics around what NREL are doing in this area. It leads the team that develops tools and data, conducts analysis that seek to clarify future electricity use and power systems with higher shares of renewables could interact to support decarbonisation and reduce costs and increase reliability. So, Elaine.
Yep, getting my microphone on so you all can hear me. All right, I think I'm set up now. Thank you for the kind introduction. So what is it that energy modelers do? Why do we spend so much time building complex models of these energy systems that don't exist? Often when I think about that question, I think about the very corny term coined by Disney, Imagineers. I think we're all Imagineers. People, modelers included, need help imagining what these future energy systems could look like. And we can't just go talk to the people who built and operated continent scale clean energy systems because they don't exist yet. So what do? We turn to well-vetted data, we turn to well-vetted models to try to paint a picture about what this could look like. The plots shown here come from the annual exercise in imagination that we at NREL call the standard scenarios. These particular plots show national scale annual generation and capacity for the entire contiguous United States. To me, the importance of plots like these is that they quickly convey how the contiguous United States power grid could evolve to be powered primarily by wind, solar, nuclear, and hydro, with some key reliability contributions from biopower and natural gas with carbon capture. However, these plots are nearly useless for actual decision makers in the United States because United States decision making is generally done at a sub-national scale. Luckily, the standard scenarios do also provide the data necessary to envision different possibilities for balancing authorities, states, and wholesale power market areas. But as we've been developing these standard scenarios and as they've matured, NREL has also recognized that there are actually a lot of different people that have a lot of different questions about what our future power systems might look like and how they might be interacting with them. For example, building owners might want to know whether they should invest in PV, or they might want to know whether they should install a heat pump now or in 5 years. Maybe they're on a system that's heavily powered by coal still, and they're not sure what the emissions kind of pencil out to be. So addressing these different kinds of questions at relevant geographic and temporal resolutions has required linking multiple tools together, such that now the standard scenarios uses 4 different tools, and we have a couple different data releases. We have our standard scenarios we've been developing for a while, and we have these new Cambium data sets that provide hourly data. So let's take a look at these different pieces. If we're just looking at the overall build out of the system, we look at 2 different models. We use DGen to tell us how much PV customers might adopt behind the meter. And that feeds into reads, which then determines the optimal utility scale investment decisions given a certain economic and policy landscape. Both of those tools answer the question of what resources should be built, but they answer that question from two different perspectives. They answer it from the customer perspective and the utility perspective. Then if we want to give more temporal resolution and provide hourly data on what the grid service values might be, what the emission rates might be, we have to dig deeper and we have to go to a production cost model. In this case, we're using Plexos to do hourly operational modeling of these envisioned future systems. And we have to do a whole bunch of additional post-processing to get metrics like the one shown here, which is a marginal long-run emission rate, which lets people on the demand side think about, how is my technology, what's the impact of my technology going to be over the next 20 or 30 years? So a second key reason to perform detailed energy modeling is to plot out very specific plans for very specific systems, being sure to take the time it takes, which is a lot, to poke and prod and make sure that the plans are solid enough to support large-scale investment decisions. One example of this kind of energy modeling is the Los Angeles 100% Renewable Energy Study, or LA 100 for short. When we released this study 2 years ago, a lot of the next steps for the Los Angeles Department of Water and Power, LADWP, were clear because the different scenarios we constructed had a lot in common. They all had a lot of demand side electrification, a lot of energy efficiency. They have flexible load. They have a lot of customer rooftop solar and some customer storage. They have a lot of wind and solar. And they have a lot of utility scale storage as well as distribution and transmission upgrades. And then to get to that last 100%, this study also made the assumption that LADWP is an island. And so to meet the last little bit, they needed renewably fueled combustion turbines to get to 100%. The scenarios had also been vetted at a lot of different levels. Although the work of fully planning LADWP's future power system is very much so ongoing. The fact that we looked at the scenarios from LA 100 from so many different angles has at least given them the confidence they need to start making those long-term investment decisions, to start investing in those things that are common across all of the pathways. They need a lot more wind and solar. They need those distribution transmission upgrades. You can just start doing that. So for the rest of my talk today, I'd like to address some of these questions here on the right. What do model linkages look like under the hood? Why are they hard to do well? And how can we improve the model linkages we need to analyze more connected energy systems? I'm going to talk about these questions from the perspective of these two case studies that I've already introduced. Reads to Plexos, which is the workflow that enables the Cambium data set, and LA 100. So first, reads to Plexos. I've introduced the standard scenarios, but this workflow of going from reads, our capacity expansion model, to Plexos, the production cost model, we use that workflow all the time for almost all of our big studies. So I just pulled a few here to highlight. There's one on the role of hydrogen in future energy systems called H2 at scale. It used reads to Plexos. The North American Renewable Integration Study, NREL, used that workflow as well. I already talked about the standard scenarios and the solar futures study. Well, what does this actually look like? This still doesn't really show you what it actually looks like, because it actually looks like a bunch of data sets in code. But this at least gives you hopefully a feeling for it's a process to go from a reads build out to a Plexos model run. We actually have to point to a different Plexos system to give us the nodal data that we're starting from. We point at that reads build out. We translate both of those pieces of data using a couple of tools, Pidge and the reads exporter. And then we combine those two pieces of data with another software tool called Beetle. That finally gives us an XML file that Plexos can turn into its native format, and then we can finally run Plexos. So that's kind of how that goes. And then of course, there's a lot of details under the hood. I think we've already heard about data. Basically, every time you do a model linkage, you have to compare, well, I'm going from this model to this model. What data does this model need? And what about this one? And there's always going to be disconnects, because if there weren't disconnects, they wouldn't be different models. And so this is just an example over here on the left of all of the different properties that we need in Plexos to do a production cost modeling run. You know, we need all these different properties for the different generators. And then, so where do we get those data? In many cases, we can take them from Reeds, because Reeds is modeling similar systems. They have a lot of the data, but they don't have all the data. So we have to fill in those gaps, and that's always a process that you have to go through. And there's also various algorithms like the one shown on the right for figuring out the details. So in this case, the flow chart on the right is showing if I have a build in Reeds, how am I going to turn that into individual units that I put in Plexos? And I think I'm not even really showing how you pick which node to put them on in Plexos, but you have all of that to deal with. So I think I hopefully have conveyed that this is a critical capability and it's complicated. And I will also tell you that it's been hard to build and it's been hard to maintain. And I kind of want to talk through a few of the reasons why, because I think they're helpful to keep in mind. We kind of already talked about data, so I won't belabor that one. But interfaces, I think as analysts, we don't often think about the concept of interfaces, but if you do a lot of software programming, you do think about the concept of interfaces. And I think they're really important for this kind of work. So to me, an interface is anything that you're expecting users of your tool to interact with. So that can just be the data sets that get produced, what format they're in, what's in them. And it can also be function calls or a command line interface. And the main thing is if I'm trying to link two models, then it's going to be a lot easier to maintain that link if the interfaces are stable. But as researchers, we don't always pay attention to that. And so I think that's one thing we can keep in mind more is how do people interact with my model? Are there things I can do to keep that interaction point stable or backward compatible or at least versioned? These are all some technical details that we sometimes overlook that can be really important for this kind of work. And then quality control. Probably everyone in this room has written a research paper, and that research paper had to go through a lot of review, and it was annoying, but it was better at the end. And I would maintain that the same is true for our data sets and the same is true for our software. If we actually review those things as part of the process of putting them together, they're going to be better, but we haven't yet made that a clear part of our culture all the time. And we're definitely working on that at NREL to review data sets and software as a usual thing we do. But of course, then we hit the final bucket, which is project planning. When we're proposing research projects, we're very interested in the shiny analysis result at the end. And it's hard to remember how much work it takes to actually put these integrated models together. It takes time and people and computing to make the links, make sure they work, review them, make them better. And so if we fail to properly account for the time it takes not just to build the models, but also to build the model linkages in that project planning phase, then we're going to fail at quality control, and we're going to fail at having stable interfaces. It's going to be harder. But these are all things that we're working on. And so on a positive note, like this is a punch list for things that our colleagues are planning to do to improve the Reeds to Plexos linkage right now, because we recognize that this is a critical capability that we would like to work more smoothly. And I'll just highlight the first two bullets. The first bullet, unit testing and error handling, is just trying to automate the process of making sure that these links work. And the second one, simplify workflow for users of Reeds to Plexos, really gets back to that interface question. How is it that users are using this tool? Is it straightforward to know what to do? How can we simplify and make this work better? All right, now I want to change gears just a little bit and think about more broadly, what would it take to do these kinds of model linkages well? And also, what are we, well, I don't know, I'm just going to put forth the vision I hope for NREL's tools, but you probably have other kinds of similar visions that would be applicable. I was talking about the standard scenarios. The standard scenarios are a national scale product. I'm going to talk about LA 100 in a little more detail in a bit, and that was a community scale analysis. I mean, I think at NREL, we would really like to be able to do this kind of grid planning work across all three of the scales shown here, national, regional, and community. But we've talked already a lot about how hard it is to keep all the data straight and to get all the tools working together. So when I think about the problem of trying to enable modeling at those different scales and have that be a smoother process, I start with, as a modeler, well, what do I need? What data do I need to build those kinds of models? Basically, for every grid model, to get started, I need a picture of the existing power system. I need an understanding of how load is going to evolve into the future. And I need my renewable resource profiles. And so I would posit that all of this would go better if we were always taking the data for those three things from the same places. So I'm just putting up the examples of projects we're working on at NREL to cover each of these pieces. We have REV there at the bottom where we get our renewable resource profiles. That's a established tool. I think they would also still say that they're maturing and sometimes feel under-resourced, but nonetheless, it's a set of tools that we lean on heavily for a lot of projects. I lead then the next two efforts, the demand side grid toolkit and GridDB, and these are envisioned as go-to places to get the load data or the grid systems data. And if all of those existed and were robust tools that users could go get, then it should be fairly straightforward to do the different scale analyses that we would like to be able to do. So if I'm thinking about a regional or a community scale model, then what I would want to do is filter down to the geography I actually care about. I'd want to leave the unit level information for the zone I'm trying to actually plan for. I might want to do some sort of aggregated zonal representation for the rest of the system. And I would really like to, I'd really like to be able to say in five years or so that we had standard scenarios for every state with combined nodal zonal representation, but that's the dream. And I think we can get there by taking all of these data sets and all of these model linkages a lot more seriously than we have in the past. Okay, so segue to LA 100, and I already showed you the spaghetti diagram. So, you know, for LA 100, we were contracted directly by LADWP. They wanted to know what they should be doing to move their system to 100% renewable energy in the next couple of decades. And they really wanted us to prove it to them that the system would be reliable. And so we kind of threw the kitchen sink at it. Up in the upper left-hand corner, you see the area where we were dealing with loads and demand response. Then in the middle, you have that capacity expansion kind of questions with DGen and RPM. And then to the right, you have a lot of reliability testing. And I think kind of going back to the previous talk, RPM, our capacity expansion model, was kind of the engine for developing all these scenarios. But then you have on the right, a lot of reliability testing to make sure that the systems built by RPM actually are going to work. And so there's a lot of iteration there. And then, yeah, there was a lot of data. So I was responsible for pulling together the load projections based on a lot of people's work. And we started with tax assessor data describing every parcel in the city, and with customer billing data describing the energy use of all the customers in LADWP. We did have all the distribution data, but of course it was challenging to work with. We had to, you know, figure out where the different customers were connected to what transformers. what distribution feeder is that on, what receiving station does that end up at. So there's just a lot of us going through a lot of data and piping it to a lot of different models. And it was the first time we did a project like this. And so we had to do, we ended up actually working with several different database technologies as we had more and more data and more users of it. But we, we went down to that parcel level. The buildings folks got California specific appliance surveys to understand what is actually in buildings in California. I don't know, there's like too much, I can't go through all of it. Just to say there were, around 100 people working with a whole lot of data. And how did we coordinate all of this? We basically coordinated this with a lot of communication. It actually started with an email from my colleague, Megan Mooney, talking about timestamps. I'm sure you have all have your horror stories about timestamps. We knew it was coming. Megan sent this email to make sure we all understood what the project time convention was, and we mostly stuck to it. We also had a data repository to manage the internal data handoffs. And then we had a SharePoint site because we were getting a lot of data from the utility. And so we had a SharePoint site where we would post our data requests for LADWP, and then they would send back data and we would track all of that. So there was just a lot of communication in the project. But like any good research project, what we, how we felt at the end of the project was that, well, now we finally know how we would actually do this project. And so we've been developing more capabilities since the project's been over based on what we learned from doing LA 100. And so, one thing I've been doing is leading the development of a new software tool for the DS grid work. And it's really focused on being able to deal with input data sets that are at different levels of resolution, output data sets that are also at different levels of resolution. Here you can see the 6 different load data handoffs for LA 100 and how they all wanted different sectors, different geographies, different time, different end uses. So we've been developing software that deals with that. We also know that we're going to be in the big data realm. So we end up with terabytes of data. So we know that we have to manage that up front. So we looked around and made a specific selection of a big data technology that we could work with. And then we're trying, as we develop more features, to just take more of the ticky-tack things off of modelers' plates. Like we want people to tell us exactly how they're representing time and then programmatically handle that. So at least it's all in one place. We want to do the same thing for units and all of those things. And then another effort that kind of grew out of LA 100 is called PIPES, the Pipeline for Integrated Projects in Energy Systems. I mentioned that we had a data repository to manage all the different handoffs between modeling teams. That was great for archiving the data sets, but it was not really responsive enough when you had people really quickly iterating between models. So we had, I kind of already mentioned the capacity expansion modelers and the production cost modelers and the power flow and the resource adequacy modelers. There were times in the project when they were all iterating really quickly, trying to get a scenario that would work. And the extra overhead of uploading data to a data repository, downloading it, was just too much, especially for, some of these data sets are a little bit big. And so some of my colleagues are developing this tool PIPES to be a project management and data management tool that would basically let modeling teams hand off data between each other without actually moving any of the data, so that it's kind of agnostic to where the data lives, but it provides just an information layer on top so that you can say, this is the modeling run for run 1, and I'm addressing this issue, such and such, and you can see when the data was checked in and all of that. So hopefully that'll make it a lot more streamlined to do this kind of integrated modeling going forward. So in conclusion, I talked about a lot of things today, but I also didn't talk about a lot of other things that are also important today. There's different kinds of integrated modeling techniques. I really just talked about scenario analysis and handing data off between models, but you could co-simulate models. You can do strategic behavioral modeling, on and on. We kind of mentioned resource adequacy, but didn't go into it in depth. In any case, all these things are also important. And yeah, I'd be happy to talk about some of these offline, and I've got a lot of colleagues here that cover a lot of these topics as well. So looking forward to chatting through the week. But what I mostly want you to take home is that as we're envisioning energy systems that are more complex and interconnected, we are going to need tools that are also more complex and interconnected. And we don't want it to be too complex, right? We need to simplify. We need to kind of bottle up that complexity in places where it's manageable. And if we're going to do that, we're going to have to put a little bit of infrastructure around it. You know, basically all these models and all these interconnections are the infrastructure that we use for envisioning, pre-testing, and communicating clean energy futures. And so we need to treat them like that infrastructure that they are, and pay attention to things like data sets, interfaces, data management layers, testing, etc. So with that, I'll conclude and thank you.
Here is Andrew Bachert. He's principal at GE Energy Consulting. He's 25 years of experience across a broad spectrum of roles. He started his career developing greenfield baseload power plants for the IPP sector, including the first merchant power financed power plant in Australia. Subsequently worked for the market monitor at MISO, where he developed his background and knowledge in power markets. And he's been working extensively on market modeling for GE Energy Consulting and external clients there. So, Andy, thanks.
So can you hear me okay? Yeah, good morning. My name is Andrew Bachert. I'm with GE Energy Consulting. Our scale of this type of modeling, it probably pales in comparison to the previous two speakers. But nonetheless, we'll go through some of our experiences. And it's interesting to see that despite the previous speakers who spoke very large and very complex data sets, and we have those, but not to the extent that they were speaking about. It's interesting to see that we're coming across the same issues, same problems, and just the model development, and it's changing over time. Just a quick background about energy consulting. We've been around for 100+ years. We have 3 primary focus areas: economic analysis, which is the group I belong to, power economics, network strategy, and equipment integration. And we also have our own software tools, or our own software suite, which we actually license to third parties. So we have a production cost model called GE Maps, which was originally developed at the very beginning of the deregulation of New York. We also have a capacity GE Mars, and then a power flow tool called GE PSLF, which I believe is primarily used here in the WEC. So we do rely on these tools quite a bit in-house because they're our own tools. And we have a software team that's actively working with us when we have studies to accommodate the specifics of a particular study. But we also use other tools as well, depending on the project. And I'll go through that a little bit later on. Just a high level. So our most complex data sets are North America. We do modeling not just for external clients, we also do modeling for clients within GE. And one of our biggest clients is Energy Financial Services. And they use our skill set and our modeling and our forecasting for both their existing assets that they have. So they have financial interest in assets throughout North America and the globe, but also if they're looking at new deals. So we work with them quite a lot, particularly on the GE map side. It's a full nodal model of North America. But we also developed models for and through the map in this graphic, for a lot of countries outside the US. Again, primarily for another internal client, or the services group for gas turbines. They want to know how often their gas turbines are running. So we have production cost models for the countries that where they have most of their gas turbines. A lot of the models we use for these is GE maps, but we also use Plexos for some of the countries. The previous speakers did touch on the need of, the changing nature of the modeling and the changing nature of the questions that are being asked of the models. And this kind of just gives you kind of a high level overview of kind of the same description of the same problem. It used to be that, in a central planned grid, you didn't really need to go into, it was for the most part, most of the modeling, at least on my side that we were doing, the production cost of modeling was sufficient. But as you start going into the decarbonization, you're starting to see that you can't necessarily rely on, say, just the peak load anymore. And so you're having to dig much deeper and rely on additional models to answer some of the questions that are popping up, either internally or with our external clients. The one area that we actually do incorporate into our North American production cost models is a gas model. So we use GPCM, which is a nodal gas model of the United States, North America specifically, Canada and the US. And that is an iterative modeling approach. So we will add all of our gas demand into the GPCM model, run the GPCM model, and then feed the results of the prices back into our maps model. And sometimes that'll reiterate several times. The interesting question that I posed to my gas modeler the other day is what is GPCM going to do when the demand for gas dries up in North America, if we ever get to that point with the electrification, particularly of the commercial and residential sectors. I don't think it's come up. I'm not really sure they're actively looking at that, but I think that's something that is going to be more prominent in the future as well. Just to give you a kind of a graphical representation of some of the issues and why we're all moving towards multiple models. Traditionally, most of the analysis was centered around peak load. And so even on a system planner, you would typically pick the peak load hour for the year in terms of diving down in terms of different analyses. Excuse me, but that's really changing because of the renewable penetration. So this was California. Sorry, I don't have the exact, I believe this was a recent year. I don't have the exact date on here. 2020, thank you. But as you note in the second graph, and it's a little bit busy, I apologize. But in the second, the green portion of the graph, you'll see that's the renewable generation and the variability that adds. And you'll see that the peak RE doesn't coincide at all with the peak load. And then you also, the next two levels is the net load ramp and then the gas capacity factor. So you have a lot of moving parts that wasn't always an issue in the past. And you really need to try to capture all that variability in the modeling going forward. And then the other side of the equation is looking at, and this is one of the reasons why we specifically have developed some what we call round trip analysis. Round trip analysis basically being the combination of a production cost model and a power flow model. And so you really, the need to address the power flow is really to address the physics side. And then the production costs, and to a lesser extent, the capacity addresses the balancing side. Note the timing at the bottom. The power flow modeling typically works in seconds to minutes. The production cost works on hours, and then the capacity expansion works on years. All of those different time elements can be an issue in terms of coordinating across different models. I wanted to highlight, and I'm more on the economic side. I don't actively work on the power flow side, but I just wanted to highlight some of the areas where we see overlap. And basically all the green check marks basically require a dispatch. So and the problem here is in the power flows, typically a power flows is either like a min load state or max load state, and they don't really optimize the dispatch of generation for either of those two analyses. So sometimes it's a judgment call, where the generators will be set at that max load state when they do the power flow, or alternatively for the min load state. But it's not really incorporating the dispatch on the system, the economic dispatch on the system. And that's why we found that having this round trip analysis is really beneficial. And the hard part is you run the production cost model, you get the dispatch, and there's another piece about deciding which hour. And I think one of the other panelists did a great job in showing that type of analysis. But once you settle on an hour that you're gonna analyze, whether it's a high renewable hour or a high peak load, but you have to then transport the dispatch decisions from the production cost model into the power flow analysis. And that's a bit of the model integration that requires a bit of time and effort. And then another slide on the different types of load flows and on the technical, what I would call on the technical side. So you have a load flow analysis. So you're really looking at the voltage on the power system, the dynamics, and then also the transient stability on the system. So those are all different types. They all require different models. So on the load flow, it tends to be more the PSSC, GE, PSLF. And then on the others, it's more the PSCAD and some of the other more detailed transient models. So I'm gonna go through just high level some of the modeling that we do in GE Maps. So GE Maps is a nodal model, and it incorporates. We represent the three primary systems in the U.S. So Eastern Interconnect, ERCOT, and WEC. And we have separate models for each of those. And the primary inputs historically, load, usually on an hourly basis. Obviously your transmission and your generation, and then the outputs are nodal prices, unit revenue, line congestion, and so on. So MAPS is not a capacity expansion model. We do incorporate some capacity expansions, and it's more through a process, and I think we primarily use Python for this, where particularly in the later portions of the forecast, where we know we need, so the model is showing that there's not enough reserve margin being met in the different markets. So we will add a layer of either new gas turbines or additional wind and solar, and particularly the wind and solar, if there's a planned target for a particular state, we'll incorporate that. But we have a kind of a iteration around the new units, and we basically judge to see if the new units are financially viable or not. And if they're not, we'll take some of them out, rerun it, until we get to a kind of a stable point where, from a financial standpoint, particularly new units, you're not going to invest in a unit if you're going to lose money. That unit would be viable in that long-term capacity expansion. And as I mentioned previously, we do iterate around a North American natural gas model. So it's another model that we do have an interface between and have to work on. Is primarily the responsibility of our fuels modeling team. But there again, there's another interface between our production cost model and the gas model. We do add, and I won't spend a lot of time on this, but we do add an additional oil price forecast and a coal price forecast to our modeling. And then the outputs and on top of that, we have a nodal transmission model. The nodal transmission models do require updates. NERC releases a new power flow, and we take those power flows and update the models about once a year. And that process in itself takes several months. So it's a very detailed process to incorporate those updates on the power flow modeling. Someone asked earlier about the validity of models. We have in the past had our GE MAPS model audited on behalf of Energy Financial Services, or one of our internal clients. They had to go through a process. This was 5 or 6 years ago, where because of the size of their assets, they had to be audited. And so we had a number of professionals and PhDs look at the algorithms of GE MAPS as well as the outputs, and we're able to verify that the model by and large does what it was supposed to do. And production cost models aren't quite as hard to validate because you have economic markets, which you can compare them to. So New York ISO, for example, PJM, California ISO, you can benchmark because they all produce, it's all cost minimization optimization. So you can benchmark to actual prices in those markets. And we generally do very well in terms of our benchmarking. We do that on a regular basis. And more detail on the transmission model. In addition to incorporating the power flows, we have to rebuild all the contingencies, interface limits. It's quite an involved process. So high level, and I don't have the details that the previous presenters provided. So we have done a number of round trip where we fed the dispatch generation from our MAPS model into either PSSC or PSLF. And as I explained before, the reason you really want to do this is you really want to capture an economic dispatch of the power grid, and then use that in your power flow analysis. And generally, the economic dispatch is going to incorporate the nuances of natural gas prices, other fuel prices, limitations on the grid, limitations on renewable resources, and then you go and would feed that back into the either PSSC or PSLF. I've worked on a couple of projects where we started for an external client overseas, and they actually gave us a power flow, and so we are actually start the modeling from scratch, straight from the power flow, and that made the round trip analysis a lot easier because we weren't starting from two different models and then trying to combine the two in terms of the round trip. So basically the naming of all the generators and the data set was pretty much already set, and they were complementary between the power flow, and at that time we were using Plexos. That's probably not always the case. That was kind of a unique situation. More often than not, you're starting with two completely different data sets. And then you're going to have to try to marry the two together for a particular analysis. We found that, one of the easiest ways, and this kind of goes back to, I think there's a question earlier, what's helpful in terms of data set maintenance and having a kind of a common approach to this type of analysis. And I had found, and I'm not going to speak for all my colleagues, but excuse me, I had found that one of the things is using a common generator naming convention, whether it's the EIA or for a lot of our overseas models, it's Platts UDI. And both of those data sets will have a specific number that will be attached to that generator. And then we can, if we're using different models or if we have clients that are using a different data set, but they are also using that numeric identifier, then it's a lot easier to do this type of analysis. I will say that some software has import-export feature. So Plexos does allow you to import PSSE power flows, but there's still a lot of work that has to be done once you import that to incorporate the line limits and contingencies and so on. And unfortunately, when you import it in the Plexos, it just adopts all the names that's in PSSE, and PSSE uses just basically generator bus names or generate the bus numbers for each of the generators. So that's one's PSSE is a bit tricky sometimes. And I highlight this because this is one of the things that we do regularly in a lot of our studies, particularly this type of nature, is we'll make sure we do some sort of a benchmarking exercise. And I think the other panelists touched on this briefly as well. This is just an example of ERCOT. We're actually in the process of modeling the North American data sets in Plexos. So we can use that more detailed capacity expansion model within Plexos. And I've been building the Plexos model off of our GE maps, and we've actually created an interface between the two that seems to be working quite well so far. And this is one of the recent efforts for ERCOT, was the benchmarking, and these were prices for 2022. And this was just comparing the two models, so maps versus Plexos. Sorry, I have to take my glasses off. So the blue is maps and the orange is Plexos. But I think that's quite a very good result overall in terms of an initial benchmarking exercise. Oh, and another one, I'm just gonna skip through that one. And then the other area, how am I doing on time? Okay, I'm gonna wrap this up. And, the other issue that we've come across is obviously sharing of the results. For example, for some of the round trip, when you're going between PSSE and Plexos or PSSE and maps, we haven't quite, at least not to my knowledge, quite developed a automated version of doing that. So it's really more taking the results, putting it into a format they can easily copy into the other model, and then proceeding. I think that would certainly be an area that we'd look to develop more in the future. We do a lot of work in Python. So some of we have software team that can build the scripts. And so that is beginning to automate that process quite a bit more. But it's still something that, at least in the past, has been more of a manual approach. I'm not going to go through this in great detail. This will just give you an example of a study we did last year. Are we making our slides available? Okay, so you'll have this, and if you have any questions. I wasn't involved in this particular study. My colleague Chrissy was working on this last year. It was for DOE, and it was basically looking at pump storage hydro. I believe in WEC. And the key that I want to illustrate here, and it was a very good study. I think the client was very happy with it. But the key here that I kind of wanted to address was, first, we developed our own internal pump storage hydro optimization tool that we then that the results were then fed into maps. And the specifics of that particular tool, because the technology we're looking at for this particular pump storage hydro was a variable generator on the hydro side. And it has a lot more capability than the typical hydro generator. Then it was fed into Plexos. There were a number of simulations run. There's a whole, I'm gonna skip ahead a little bit. So here you can see there was a whole kind of matrix of scenarios that were used to kind of pinpoint the range of results, if you will, for the particular pump storage. But the other piece that I wanted to highlight in this was that we then used PSLF to evaluate on the transmission side and actually look at the benefits of pump storage hydro on the transmission network. And then also we did, and again, I'm gonna skip through a couple of slides, but also we did, we used our GE Mars software to look at on the capacity side and adequacy for the pump storage hydro. So there was really 4 different kind of tools that we used for this particular study. And there was this whole kind of integrating between different models. I unfortunately didn't work on it, so I couldn't provide great detail on how that worked out between the different sets. But I think the results of the study went quite well. So I'll skip the last couple pages and finish on that one.
We're going to move to the shorter, quick presentation part of the agenda here, and each of the folks here will take a few minutes, 7 to 10 minutes, to go through some of the issues that they're seeing in a particular area. Just for folks looking at the time, we have a 2-hour lunch schedule, so I think it's okay to take 15 minutes from that, and we're going to do that. And Charlie's okay with that. So we'll get into this. So we will have time for panel discussion here at the end. Don't worry, as you see the time getting closer to noon. So first of the panelists, Angie Bond-Simpson, who's an earth and climate scientist by education and 20 years experience in water and power utility planning at SRP. Marrying these experiences together, along with her propensity to be a thorn in the side of others, she takes pride in imagining the future power system, working cross-functionally to clear hurdles and driving the type of change customers desire. She's leading SRP's transition from integrated resource planning to integrated system planning, which incorporates customer programs, T&D, and generation planning and operations, and seeks to maintain SRP's high standard of safe, reliable, affordable power while driving a low carbon future. So.
All right, thanks, Aidan. Can everybody hear me okay? All right, what a beautiful day to be in a windowless conference room. I'm going to try to bring the energy up a little bit. I have a different type of talk than the previous 3 speakers. So at SRP, and I'll talk a little bit about who SRP is, we've really been trying to implement this transition from integrated resource planning to integrated system planning. And I can't tell you how great it is. Like, I feel like I belong to this audience. When I go back to SRP, I'm a little bit of the weirdo that's driving the change and talking about Aidan mentioned the thorn in the side of others, of a call to action, right? That we need to be doing better, and we need to be thinking more holistically. We need to be breaking down silos. Our plans need to be operable. And so it's really great to be in a room full of people that are going through the same struggles. And I really believe that, we put the best and brightest minds on this. And at some point in time, we're going to be talking about, recall many years ago when we were trying to figure this out, and now we've got it figured out. All right, so my talk, these slides are really just guides for me not to ramble in my 8 minutes. So I won't talk about all the content on the slides you see, but I'm going to try to set up, who SRP is, because that paints the reason why we're doing system-wide planning. And then I'll talk a little bit about what that means and I'll kind of leave you with the implementation thing. So I'm going to set up the frame of the puzzle, and then your questions are going to be the puzzle pieces, during the panel that I try to get a bigger vision here. So SRP is the third largest public power utility in the nation. And what that means is we are a cost to serve. We serve our customers. We have no investors. And so all of the opportunities, all of the risks, all of the cost are directly passed down to our customers. So that means that we want to be very responsible with the infrastructure we cite, the programs we develop, because they have to persist and sustain no matter what the future holds. Right? We think about system optimization as a possibility, and we want to be here for that. But I'm here to tell you that optimization right now, like Elaine said, is in the imagination space for us. To be very clear, we are looking at the behaviors, the good decision-making processes, the good analysis, how to think of things differently than we have in the past. We provide affordable, reliable water and power to about 2 million customers. That's located mostly in metropolitan Phoenix area. And the bragging portion of my talk will be to say that over the last 25 years, we got really, really good at that. So we are consistently ranked the highest utility in the West for customer satisfaction, both in business and in residential customers. That's really important because those customers are growing at 3 times the national average in Phoenix. So we have a tremendous load that is coming our way that we have to plan for, and making sure that we get that right for both the residential and business customers is part of the vision of integrated system planning. I won't talk about the water, but if you guys have seen in the news, we are spilling over 30,000 cubic feet per second over our dams today. And that's good from a generation perspective. It's also good from vibrancy and being able to survive in the desert. So when we think about where SRP is going, I talk about that humble brag with customer service and customer satisfaction. But again, that paints our picture. So if we are thinking about decarbonizing in the future, what we don't want to do is sacrifice that customer satisfaction. So we want to make sure not just to do it, but to hit it out of the park, to make sure it's just as reliable and affordable for those customers as they experience today. So today's energy mix, we have about 3/4 of our energy being delivered from conventional generating resources. So that means that we are using those resources for a large part of our central reliability service capability. And as we transition to the future in 2035, we believe that's going to flip. Our vision that we see here is that renewables will then take up about 3/4 of our annual energy supply. Right, and so all this transition, along with how the grid is evolving and the different needs from the grid, just means that everything's getting more complex. Everybody in this room knows that, right? I don't have to go there. But what I do want people to think about in this room is it's not just about hope. It's not just about imagination. It's not just about the feasibility. But at SRP, my job is making sure that that can work, that the operators, the traders, the dispatchers on the distribution side have a chance to think about what this future looks like, to problem solve, to mitigate, and to even vocalize concerns that they might have about that future. So what you're probably interested in, and we've seen in the previous 3 presentations, is not really what I'm going to spend a lot of time on today. We have this for our first ever integrated system plan. We have a framework of analysis. This was co-developed between SRP and E3 Consulting. We're very happy with this. This is our blueprint for how we're going to do things. This is the 3rd step in the process for integrated system planning at SRP. This is the analysis process. What we have spent a lot of time on is alignment and documentation of a study plan. And I know those aren't the sexy things we want to talk about today, but it took so much time to get to this point that I think it's something that should be considered when we're talking about integrated planning for the future. So to get here, we started in January of 2019 to align on assumptions. November of 2021 is when we were finished aligning on assumptions of what it was we wanted to do and accomplish. That meant that we were taking our established 2035 goals and achieving them or exceeding them at the best customer value. We weren't looking at changing them. We weren't looking at getting, better. We weren't looking at trying to think about regionalization, that the scope had to be somewhat small and discrete. From November 2021 to April of 2022 is when we developed our study plan and documented all of those assumptions, right? So it took almost 3 years to get to the point where we were ready for the analysis, right? So think about that, right? And we are asking those people that have contributed and been rewarded for good customer satisfaction to change their blueprint and to change what they are doing and how they analyze. We're asking them to collaborate, and collaboration when you're opening up those silos just takes more time at first. So our first integrated system plan is being analyzed through a scenario planning process. I'm sure I'll get some questions about that. And if not, you can always ask me later on. But the thing that I would like to draw your eye to is that last bullet. So the integrated system plan thinks about the new capabilities, tools for the future. This is more than just the modeling exercise. It's knowing that there's going to be new engineering standards. There's going to be new methodologies we haven't thought about, new data needs. I think both Elaine and Anish talked about that. New abilities to process the amount of data. And of course, new reasons or new opportunities to validate those data sets as well. We do have a study plan that is out there for anybody's review. So if you Google SRP ISP, you can obtain the study plan, and you can see, at least at a high level, the scenarios we're considering. We also have all of our assumptions, constraints put in there as well for this first ever planning process. I like to say that this is a pilot, that this is our first chance at kind of duct taping and baling wiring the system together. But this is the foundation that we need to innovate in the future. All right, my last slide. For the implementation considerations, what I will challenge everybody to do in the room this week, when you think about science, right, your propensity is probably going to go to physics, maybe climate science, but you also have to think about behavioral science, right? Because if you want integrated planning, if you want the silos to be broken open and the behaviors to collaborate to persist, you have to get that level of buy-in, right? And so the first thing that I will leave you with on the implementation is change is hard. It's harder than you think. Not everybody's going to be on board, particularly those that have not been rewarded for innovating or having new methods or collaborating before. And you need everybody to be on board for it, or you get kind of accused of bulldozing. It's going to take longer than you think, much, much longer. So I think I gave you my time scale. And part of that is because you don't have a lot of multidisciplinary experience that totally understands everything. So we spent about a day on the word criteria early on in our development. And that was a really, really painful day. And then lastly, every one of you will hear me say at some point in time, I think Leanne, Arifine, those at SRP have heard me say it over and over and over again. This is messy, and you have to embrace the messiness. It's not going to be perfect. You are going to learn so many things. So resist the need to Monday morning quarterback because it's the right thing to do, and we're in the thick of it. So look forward to the questions and the additional panelists.
Panelist there is Armando Figueroa Acevedo from MISO. He holds a doctorate degree from Iowa State University, registered professional engineer. And at MISO, he focused on strategic assessments related to resource adequacy and transmission planning. So very suitable type of work for the discussion here. He's a part-time professor at University of Puerto Rico, MIGAS, and the chair of the IEEE RA working group.
Right. Thank you, Aiden. Morning, everyone. So I'm going to talk this morning about the renewable integration impact assessment. You're probably familiar with that study. We have presented it in the past here at ESIG. This time we're going to focus on how we did it. Okay, so a few slides that I have just to go into the details and the process and the methods, and more importantly, the data linkage and tool linkage between all those focus areas. So I'm going to briefly talk about RIA, just as a refresh or an overview, and then I'm going to jump into the specifics of the study. So for the ones that are not familiar with REA, REA stands for Renewable Integration Impact Assessment, and it focused on three main areas, call it focus areas. One is operating reliability. We define it as the ability to withstand unanticipated component losses or disturbances on the system at the system level, MISO wide. Energy adequacy, the ability to provide energy in all operating hours continuously throughout the year. So this incorporates transmission, nodal transmission, also ramping. So some of the operational components as well that are normally not accounted for in the resource adequacy area. And then resource adequacy, I'm starting from the finish to the end here, from the finish to the beginning here, having sufficient resources to reliably serve demand and meet the 1 day in 10 loss of load expectation. Okay, so this is a graph that shows the final deliverable, the outcome of the REA study. So we measure complexity as a function of renewable integration, and we found an inflection point between the 30 to 40% at the MISO, and that percent it's energy. Okay, so it's annual energy supplied by wind and solar resources. So we developed a question that we asked ourselves at the beginning is how do we study all these complexities, right? And we started this 6 or 7 years ago when we wrap up the study 3 years ago when we published it. So we asked ourselves, how do we do this, right? With all these interactions and all the complexities that other panelists have talked about in previous talks. So we developed this robust, robust data management process to link tools, but more importantly, or more broadly, to coordinate between the different areas, right? And I'm not gonna say repeat what other panelists have been saying. It's a similar process. It's a loop, a feedback loop, right? Where you have different tools and assessments that help inform other tools, right? So you go from a high level to a more granular type of analysis, normally higher fidelity from modeling perspective, and then you close the loop and iterate until you find a solution that meets your criteria. In this case, we start with our, as some of the others have said, with the portfolio, right? Assumptions. We made assumptions about the mix, generation, wind and solar, and also the siting. So where those are going to be located at. Then we perform a resource adequacy assessment to identify retirements. And then that gets passed into a production cost, okay? So that we can assess the energy adequacy portion of the system. So nodal transmission, look at things like curtailment, prices, congestion in the system as well. And then, so that's how we met the energy adequacy, if you will, focus area. Then we pass that information to the reliability, right? So this is all the voltage related analysis, the thermal overloads, and everything that it's on the AC side of power systems. And then we finally close the loop, and then we find solutions, right? So once we study the different, we call inflection points on the system. So we find issues on the system. So that includes thermal voltages, again, curtailment, potentially ramping issues, resource adequacy issue. Then we close the loop by performing a solution assessment as well. So this include either adding capacity or redispatching or adding transmission as well or storage, so that we can move to the next milestone as we refer to in the REA study. Okay, so that's a high level that process diagram. One of the most data and process intensive parts of the REA process was this production cost to reliability loop. Okay, so especially on the handoff side of things and processing, and it required a lot of automation in the back end. And one of the takeaways from this presentation that I would like all of you to take home is that visualization is very important. Okay, and it helps us. We leverage a lot of the tools from NREL to not only talk to our stakeholders and demonstrate the results, but also for our own internal processes, right? To debug, to verify, to benchmark, and more importantly, to understand the system complexities at higher level of renewable penetration at MISO. So this is kind of connecting the dots a little bit on terms of the handoffs. Start with the siting rights, and then the question is, we asked there, it's what's the location and mix of renewables. Then that gets passed into a resource adequacy assessment where we calculate capacity value, so that we can answer the question of how much or how many retirements right, for each one of the renewable penetration levels that we study. So we study from 10% all the way to 50% renewable penetration at MISO. And then finally, which risky conditions, and some of the panelists have already talked about that, or different methods, right, of selecting the risky operating conditions based on not only peak load or even net peak load conditions, but the most risky conditions, right, that incorporates outages and some of the other components that normally are not accounted for in the input data side of things. So this is, I'll say, one of the best tools that we incorporate and that we leverage from NREL's Kaleidoscope. Probably familiar with this. Images and videos. These were used in the ERGIS and ARIS and SIMS interconnection study. So we customize it for our own footprint and our own study. And it doesn't only provide a visual on how the system is behaving, but it also helps us understand the behavior, more from a data verification perspective and handoff perspective. So we found a lot of value in this type of application when doing RIA. I added some loop here. I'm not going to go into the details, but as every engineer, we have a loop to connect the dots and show how the process work in this case. So lessons learned, I'll wrap it up with this one. I think the first one, it's a well-known for everyone, harmonizing data at the beginning, right? Synchronizing weather years, especially in the resource adequacy part of the analysis. Want to make sure that data is synchronized so we can capture correlated events, right? When it's very hot, want to make sure that we capture the behavior of wind, solar, and thermal when those conditions occur. Same with extreme weather on the cold side. We think that the use of different tools provide insights to specific questions and adds a layer of verification as well. So we found it useful to use different tools, acknowledging the complexities, right, with the handoffs and all that. But we found that visualization is key, not only for presenting to stakeholders, but also for internal purposes, for what we call our internal stakeholders, right? So we can be able to understand and educate internal stakeholders as well. And then finally, leveraging open source codes from NREL allowed for better understanding of not only the outputs, but also the input data, more for verification purposes. So with that, I'm going to stop here and thank you very much. Take any questions that you may have now.
All right, moving on. The next panelist here is Carlo Brancucci. Carlo's CEO and co-founder of encoord, a software company helping energy utilities plan for the energy transition with an integrated planning solution. He's been working in energy modeling for planning in the US and Europe since 2010. And Carlo and I have something in common in that we both became US citizens in the past week. So that's kind of.
Thank you very much, Aidan, for the introduction, and thank you, Isaac, for the opportunity to be here today and share with you encoord's perspective on integrated planning. First, I want to start with how we define integrated planning. For us, integrated planning is the coordination of planning processes across different energy networks, such as electricity, gas, or thermal networks, across transmission and distribution, or across generation and transmission, but also across economics and reliability, and across short-term operational decisions and long-term strategic decisions. We believe that the coordination of planning processes that today are siloed is absolutely necessary to transition to an integrated energy system that can transition to a decarbonized future, that can leverage new technologies, and that can be more reliable and resilient. Today, we've heard from especially the first three presentations, how challenging integrated planning can be. And the goal for me today is to try to explain with my own words, in the simplest way possible, why integrated planning is hard. We believe integrated planning is hard for 4 reasons: people, process, software, and data. Let's start with people. As you know, different planning teams at utilities or energy network operators and planners, they all are used to or care about different goals have different perspectives, use different software, and use different data. They are not used to speak to each other and often see it in different buildings, in different cities in many cases. They really speak different technical languages. So when they try to talk to each other, sometimes they get lost in translation. Second, process. Different planning teams are used to different planning processes. These planning processes can be as different as an IKEA furniture instruction manual and an IEEE process diagram. An integrated plan or a planning processes are different planning team. The planning teams are used to have different levels or needs of optimization models, simulation models, data analysis tools, sensitivity analysis. So they really work and operate with a very different mindset. Software, different planning teams, as you know, use different modeling software. This software were never developed to talk to each other. And we've heard today the need for iterations for this software to communicate. And finally, data. You should try to find the 5 differences between these 2 images. The different planning teams that model the same network often rely on different data sets. However, they are modeling the same system. These data sets, neither of them are wrong. Neither of these pictures is better or more correct than the other. They're just different. And sometimes the differences are so subtle that are hard to appreciate. And that creates inconsistencies in a potential integrated planning process. So planning departments at an electric and gas utility use different data sets and different modeling software to inform their both operational and strategic planning decisions. Here I show you an incomplete example of electric transmission, distribution, generation, and gas planning teams within a single utility. They all use a wide range of different tools. Each tool uses a different data input, and these tools are not meant to communicate with each other. And this is not a comprehensive overview. I am not showing other modeling needs that include capacity expansion, resource adequacy analysis, or power system dynamics, as we've heard today during the previous presentations. So at encoord, we believe that the best solution for integrated planning is first an integrated planning team like SRP has. Second is an integrated planning process like SRP, and I'm sorry, I keep citing SRP, but it was a great example of a process that is being established recently, but also an integrated planning software that has and uses and builds a consistent single data set. The integrated planning software should not replace existing planning software, but it should leverage the data sets and the great work and expertise that has been developed over the decades with the other planning software. The integrated planning software should be able to import data from existing siloed modeling software that have been used for decades. Integrated planning software will allow utilities to inform the different planning processes that cross electric generation as well as electric and gas transmission and distribution in a single platform, relying on a single consistent data structure. Utility planners will be able to answer questions that now they cannot answer, or that in order to answer, they need to go through the very challenging need to link and iterate between siloed modeling software. And I want to show with you, before I end, 4 examples of this type of questions that they can answer. An integrated planning software that can import data from electric transmission and distribution simulation software can now answer questions by running power flow simulations of what is the impact of distributed resources connected to the local distribution network, like distributed generation, distributed storage, electric vehicle charging, and others on the transmission network. An integrated planning software that can run both power flow simulations and production cost modeling using the same input data set can now understand the feasibility of different dispatch solutions that are becoming more diverse and harder to forecast as we integrate more variability and uncertainty in our system with renewables and storage. Electricity planners are going to be able, with an integrated planning software, to quantify, assess, and prepare for potential gas offtake constraints at gas-fired power plants by iterating between production cost models and gas hydraulic simulations. This is becoming more relevant as we see the more frequent occurrence of extreme cold events like Storm Elliott last December, or the famous unfortunate storm that caused loss of life in February 2021 in Texas. And my final example is about electric and gas utilities that want to decarbonize. They need to do something about their gas customers. One option, among others, is to electrify these heating demands. With an integrated planning software, they can see and model and iterate between their electric distribution and gas distribution infrastructure models to quantify the impacts on avoided gas infrastructure reinforcement and additional electric infrastructure costs. I want to add by saying that the urgent need for integrated planning is the reason why we co-founded NCORD. As you probably guess, NCORD stands for Energy Coordination. We believe that the energy transition requires an integrated planning process that allows today's energy systems to leverage new technologies and integrate them reliably to find a pathway to decarbonization and to be more resilient against extreme events, either weather-related or geopolitically related, as we've seen lately, unfortunately. And I want to end by saying that the future of planning is integrated, as it has been shown here today in this session. And there is a clear need for integrated planning teams, processes, software, and data. Thank you. So it can be both.
Well, John's getting ready. John Goldis is an expert in systems engineering with a background in computer science and economics. And since 2007, has been providing expert consulting and research in power markets design analysis, consulting including generation transmission, wind integration studies, market power, resource adequacy, and other things. He's also a co-founder and CTO of Newton Energy Group, responsible for the implementation of high-performance computing to optimize software processes related to energy system modeling. So John's going to give us some of his thoughts on this topic.
Yeah. Thanks, everyone. I'll try not to repeat a lot of what's already been said. I think sort of from a kind of tooling perspective, we share a lot of the same philosophy, our friends at encoord. So I'll go over a little bit of, I guess, what our view is of these planning processes. I think pretty much what everyone already understands, and talk a little bit about the challenges that we see from our perspective and just some examples of addressing those. So, this is basically the landscape that we see, along with the timeframes, going from resource adequacy to short-term reliability, capacity expansion, all of these sort of processes that kind of most of you guys are addressing in your work. And so kind of the challenges, right, with integration. One, most people use different tools, even in the same organization, different tools in different sort of groups because the audiences are different. Those tools are generally not communicating with each other or not communicating with each other very well. And that's partly just historical, and partly it's just very hard to get tools to communicate with each other. They make different assumptions even around the same exact input data. How that's processed can be very different. You'll get different results. Trying to align those results is just not a lot of fun. And kind of from the data perspective, ensuring consistency between those data sets, especially typically they've been calibrated by different groups, calibrated slightly differently because the tools are different, which means the way the data is represented is different. Getting those data sets aligned is probably even harder. And then just coordinating an interaction between the actual processes You know, oftentimes you can't really do this in a single simulation. If you're trying to do real-time sort of simulation with capacity expansion, no one's gonna suggest to do that as a single optimization, right? So getting the processes in place to get these sort of interactions to work consistently together. So, okay, kind of where our perspective is on improving this. This first point is basically just a throwaway because that's never going to happen ever. But you know, essentially, the way we see it, I think, same is basically that you need a single software and a single sort of data structures that will allow this coordination. Because I think, as Angie said, right, you know, they're different teams, they all do different things. You know, there's almost impossible to get everyone on the same page and agree, right? But if you have a single source of truth, so to speak, and a single tool, or maybe just a limited set of tools, then everyone has to work off of the same sort of framework. You're sort of forced into that, which, you know, at least sort of then gets everyone kind of going off the same set of assumptions and a set of results. And even if they're not communicating to each other, the kind of results of the simulations of the different processes are at least at some level kind of consistent. And the last piece is, I think, very important, is the automation of the linkage between these processes, which I know kind of everyone has their own Python scripts that take stuff from one tool, put it into another tool, requires a ton of iteration, you know, and sort of having good processes, even within a single platform, to do this automation, you know, whether it's capacity expansion or production cost modeling, reliability analysis, the capacity expansion, all of these sort of processes that should be automated, you know, so that people aren't manually essentially fudging results of one simulation and putting them as inputs into another, which from my personal history in consulting is how a lot of things were done. You know, it was post-run adjustment, what we used to call them. And so just as an example, you know, how we see a lot of these workflows from kind of our customers and from my history of doing these things, you know, it's sort of kind of what's shown on this sort of diagram in terms of the processes that are followed, right? And the key here is that it's often not just a single iteration, right? You sort of go through this, whether it's a single sort of simulation that may be capturing production cost modeling and or some day ahead type of functionality in real time sort of assessment in one simulation, or if it's sort of capacity expansion and resource adequacy. You know, oftentimes you get the results, you go into the next stage, it's not consistent, or it's almost never consistent, and you go back and you iterate, right? And sort of having a process that sort of aids that, where it's not manual and you know, requires a lot of human effort, which often leads to simple mistakes throughout the whole thing, is very important. The last thing I'll probably say is that, you know, having not only sort of you know, a single platform or a single tool that does this, is having sort of consistent representation of the system across all these processes. So if you're doing capacity expansion and you're not representing anything nodally, it's just zonal pipes and bubbles, then you go to production cost modeling. Where do you put those generators? You put them somewhere, it doesn't work, it causes transmission constraints. You got to go back, do capacity expansion again, tweak some random assumptions about I don't know what, get some different results. In the end, you kind of have to throw those out and just cite the generators at load centers. And it's sort of okay, but not great. Same with resource adequacy. If you're not doing it nodally and you're just doing pipes and bubbles, then again, you get into the nodal site. What do? You have to cluster, you have to do something else, creates a lot of inefficiency. So I think having sort of a consistent set of data and tools is one thing, but then having a consistent representation of your processes that actually reflect what operators do and how the market's actually operated is very important. So I think everything else I wanted to say was covered by everyone else. So I'm going to stop there and get us